Hey guys, this is part 5 of the series on energy-based models or EBMs. In this video, I will show you how EBMs work as generative models, and I will walk you through a fully worked one-dimensional example where we actually train a tiny EBM from scratch. Energy-based models have become an exciting tool for generative modeling, and what makes them special is how naturally they connect to ideas straight out of statistical mechanics. But first, let's specify what is a generative model at all. Suppose we have a dataset of samples x1, x2 up to xn. These can be images, sentences, molecular configurations, anything, and they are drawn from some unknown data distribution. A generative model is a model that tries to learn this distribution of a dataset. Once we have a good approximation, we can generate or sample new data points that look like they came from the original dataset. That is the basis of how Google's NanoBanana or OpenAI's GPT-Image2 work. Now, the central difficulty in all generative models is that this data distribution lives in an enormously high dimensional space, and probability distributions must satisfy a strict constraint. They must be non-negative and they must integrate to one. Different families of generative models handle this normalization constant in different ways. I categorize them as those that try to somehow compute the integral and those that try to avoid it. In the first category, we have autoregressive models, which factorize the distribution into a product of conditionals, where each conditional is normalized by construction. So the full integral comes for free. We also have VAEs, which optimize a variational bound, so they compute the integral only approximately by bounding it from below. And we have normalizing flows, which use invertible transformations with tractable Jacobians, giving an exact computable density. In the second category, we have diffusion models, which avoid the density entirely and learn only its score through a chain of Gaussian denoising steps. And finally, we have energy-based models, which take arguably the most radical approach. They simply refuse to normalize. Let's now understand generative EBMs through an example. Let's assume the true distribution of a dataset has a Gaussian form with the mean of 0 and variance of 1. Here, we are acting as God. Otherwise, for a real-world dataset, we never know the true distribution. However, after using a statistical inference method applied to the dataset, we find a slightly different means and variances. For a Gaussian distribution, the energy function has the following form. It is x minus mu squared divided by 2 sigma squared. To derive it, simply compare the probability distribution of a Gaussian distribution and that of an EBM. Let's first plot these distributions. Here, I have the true distribution, which is a Gaussian with mean 0 and standard deviation 1, and 3 inferred distributions that get progressively worse. The first one has a mean of 0.5 and a standard deviation of 1.1. The second has mean 1 and the standard deviation 1.3. And the third has mean 1.5 and the standard deviation 1.6. As you can see, each inferred distribution drifts further away from the true one. Now, to make our model distribution match the true data distribution, we want to minimize the difference between them. This is typically done by minimizing the cross-entropy between the true distribution and the model distribution. The cross-entropy is this integral here, and when we plug in the Boltzmann form of the model distribution, it splits into two terms. The expectation of the energy under the true distribution plus the log of the normalization constant z. Let's now compute the cross-entropy for each of the three inference methods in this plot. In this code, I first define the true distribution, then the three inferred ones, then I compute the cross-entropy by numerical integration, and I also compute the expected energy and the log of z separately, so we can see how the two terms of the equation add up. Looking at the printed table, the cross-entropy of the true distribution with itself is about 1.42, and that is the lower bound. No model can do better than this. Then, as the inferred distributions get worse, the cross-entropy grows. Inferred 1 gives about 1.53, inferred 2 gives about 1.77, and inferred 3 gives about 2.02. Note that for the example above, the free parameters theta refer to mu and sigma. As you can see from the table, the cross-entropy depends on the values of theta. Since ideally we want our model distribution to be closest to the true distribution, we want to choose the values of the theta such that the cross-entropy returns the minimum value. Therefore, our loss function in generative EBMs is usually the cross-entropy. To minimize the cross-entropy, we take derivatives of it with respect to theta. In the example above, we take two derivatives, once with respect to mu and another time with respect to sigma, and we set them to 0. This will give us a set of equations which we can solve to find the optimal values of theta. Let's now take the gradient of the loss function step by step. Since the true distribution is not a function of theta, the derivative passes through the first expectation. And after a straightforward calculation, the second term reduces to the negative of the expectation value of the same derivative, but this time under the model's distribution and not the true distribution. Putting these together, the gradient of the cross-entropy beautifully simplifies to the difference of two expectations of the same term. One expectation is over the true distribution and the other over the model. Computing the right-hand side of this equation is the main task in training generative EBMs. The first term is the expectation over the true data. We can easily estimate this by averaging the derivative of the energy over our training dataset. The second term is the expectation over our model's distribution. As you will see in the rest of the course, if data has a very high dimension, computing this term will become challenging, since we need to know the normalization constant z, and that requires solving a very high dimensional integral over the entire space. In this case, a standard numerical integration is practically impossible. Let's now make all of the above concrete with a fully worked one-dimensional example. Let's first recap. The gradient of our loss is a difference of two expectation values. The first is an average over the data, and the second is an average over model samples. Here is an overview of how we are going to compute this. First, we generate a dataset of 1000 points from the true distribution, which is a Gaussian with mean 0 and the standard deviation 1. Note that in reality, we observe a system to collect this dataset. But since we know the true distribution here, we simply generate the dataset. Second, we estimate the first expectation by averaging over the dataset. Third, we estimate the second expectation with a simple Monte Carlo method, which means averaging over samples drawn from the model. And fourth, we put the two together and solve the system of equations to find the optimal mu and sigma. Now, let's begin step 1, generating the training dataset. We draw 1000 samples from the true distribution and plot them as a histogram. The x-axis shows the single column of our dataset. The y-axis shows how often the corresponding x value appears in the rows of the dataset. This histogram of samples is the only thing our training algorithm is allowed to see. The important point to keep in mind is that in the following, the training algorithm does not know the true mu and sigma. Also, I should mention that for this plot, I generated the samples using a random number generator with a fixed seed, and then I plot the histogram of the data together with the true density as a dashed red line. The printed output tells us the sample mean is about minus 0.03 and the sample standard deviation is about 0.99. Notice that these are close to, but not exactly 0 and 1. With a finite dataset, this is the best any method can hope to recover. Now, step 2, data expectation of the gradients of the energy. For the Gaussian energy with parameters mu and sigma, the two components of the gradient are the following. The derivative with respect to mu is minus x minus mu over sigma squared, and the derivative with respect to sigma is minus x minus mu squared over sigma cubed. The first expectation in the gradient of the cross-entropy is over the true distribution, and this is exactly what our dataset gives us for free. We just average the gradient over all the data points. At the beginning, before the training, we start with an initial guess for the values of theta. We set mu equal to 2 and sigma equal to 2 as well, which is a deliberately wrong guess. In this code, I define a function that computes the two gradients of the energy and another function that averages them over the dataset. Then I evaluate them at the wrong initial guess. The output shows that at this initial guess, the data expectation of the mu gradient is about 0.51, and the data expectation of the sigma gradient is about minus 0.64. Now, step 3, the Monte Carlo estimate of the model expectation. The second expectation that we need to compute is over the model's distribution. In general, this is the hard part of training EBMs because it requires sampling from the Boltzmann distribution without knowing Z. In our one-dimensional Gaussian toy model, we are lucky. We know Z because the model distribution is just a one-dimensional Gaussian with mean mu and standard deviation sigma, for which the normalization constant is known, and therefore we can sample directly. The Monte Carlo estimator is then a plain average over model samples. So let's generate a sampled dataset using the model distribution, again for the same initial guess of mu equals 2 and sigma equals 2. Next, we use the sampled dataset to compute the expectations of the derivatives. In this code, I draw 5,000 samples from the model, compute the gradients on those samples, and average them. I also check how fast the Monte Carlo estimate converges by repeating it for increasing numbers of samples and plotting the result. The output shows the estimate of the mu gradient is about 0.002, where the exact value is 0, and the estimate of the sigma gradient is about minus 0.51, where the exact value is minus 0.5. Looking at the plot, the estimator is noisy for small numbers of samples, but settles onto the exact value as the number of samples grows. And now, step 4. We put the two expectations together and solve for the optimal theta. We now have numerical access to both terms, so we can assemble the full gradient of the loss function for any given theta parameter. Our goal is to find the optimal parameters that minimize the cross-entropy using the gradient descent method. Since theta in this example is the mu and sigma of Gaussian distribution, we start from the deliberately bad initial guess of mu equals 2 and sigma equals 2. Next, we compute the gradient above, update the values using the gradient descent method, and repeat. When the two expectations balance each other, the gradient vanishes and we have reached the solution of the system. In this code, I run 300 steps of gradient descent. At each step, I compute the data expectation, then the Monte Carlo model expectation, subtract them to get the gradient, and update the parameters. I also record the trajectory so we can plot it. After 300 steps, the estimated mu is about minus 0.029, which is close to 0. That is the value of the same parameter in the true distribution, which in practical settings only God knows. The estimated sigma is about 0.985, which is close to the true value of 1. Looking at the two plots, both parameters glide from the bad initial guess toward the two values. The small residual wiggle around the dashed line is Monte Carlo noise. Let's now plot the dataset together with the learned distribution and our initially guessed distribution. You can see the trained EBM sits right on top of the data histogram, while the initial guess, shown as a dotted gray curve, is far off. Now that we are done with the practical method of learning the free parameters of our model using a given dataset, let's build the analytical intuition as well. I call this the God view because, unlike the method that we just discussed, This is only possible if we were God and knew the true distribution of a dataset. Let's remind ourselves that the energy function in a one-dimensional Gaussian distribution is x minus mu squared over 2 sigma squared, and the normalization constant is the square root of 2 pi sigma squared. It is quite easy to take derivatives of the energy function with respect to the free parameters. The derivative with respect to mu is minus x minus mu over sigma squared, and the derivative with respect to sigma is minus x minus mu squared over sigma cubed. So to find the optimal values for the free parameters, we need to solve two equations. The derivative of h with respect to mu equals 0, and the derivatives of h with respect to sigma equals 0. In one dimension, it is easy to calculate the integrals related to the expectations analytically. This will give us a deep intuition. Note that for this example, we assumed that the true distribution has a Gaussian form with mean 0 and variance 1. That was us acting as God. However, now we want to forget the ground truth and no longer act as God, but act as human and model our data using a Gaussian distribution. That is the best a human can do. But now the mean and variance are unknown, to be determined by minimizing the cross-entropy. Let's start with the gradient with respect to mu. The data side expectation is an integral of the true distribution times the derivative of the energy. Pulling out the constants, this becomes minus the true mean minus mu over sigma squared. The model side expectation is the same integral, but now under the model distribution. And since the expectation of x under the model is just mu, this term is exactly 0. Together, the derivative of h with respect to mu is mu minus the true mean divided by sigma squared. Now, the gradient with respect to sigma. The data side expectation requires the second moment of x minus mu under the true distribution. After a straightforward calculation, the result will look like the following. The model side expectation uses the fact that the variance of the model itself is sigma squared. So this term becomes minus sigma squared over sigma cubed, which is just minus 1 over sigma. Together, the derivative of h with respect to sigma is 1 over sigma minus the following. Now that we have the derivatives of h, we set both to 0 and solve the system of equations. Setting the mu derivative to 0 immediately gives mu equal to the true mean. Setting the sigma derivative to 0 and multiplying 2 by sigma cubed gives sigma squared equal to the true variance plus the squared difference of the means. Substituting the first result into the second kills that squared difference term, and we get sigma equal to the true standard deviation. So the unique stationary point of the cross entropy is mu equal to mu star and sigma equal to sigma star. In other words, gradient descent on the cross entropy recovers the true distribution exactly. Note that in this example, we acted as both God and human, but in reality, we can only act as a human. That means we don't even know the form of the true distribution. The practical method to estimate the expectation using the true distribution is to compute the term for each row of the dataset and average, which gives us a function of theta. The second term is the expectation over our model's distribution, and it involves the normalization constant z, which itself is an integral over the entire space. If the data has a very high dimension, computing this term will become challenging, since we need to know z, and that requires solving a very high dimensional integral. In this case, a standard numerical integration is practically impossible, so we need to use other numerical methods for training. With this, I conclude part 5 of the EBM video series. And here is a question for you before I get into those numerical sampling methods. In our toy example, we could sample from the model directly because it was a simple Gaussian. How do you think we can sample from a model distribution when the energy function is a deep neural network and we cannot compute Z? Write your answers in the comments below. And please send this video to someone who might find it useful. Your word of mouth is the best way to support me in creating more videos like this. And finally, I run a mentorship program where I can help you apply these models in your projects, whether it is a portfolio project to boost your career or a business project to build a better product and increase your revenue. If interested, use the link in the description below to book a short call. Take care and see you in the next video.